In this video, this is Dr. Delahousie, and I'm going over exam number 2 for the summer 2013 session of MAE 3013, both an in-class and a web session. So this is my solution to exam number 2, and I'll go over the details with you. I'm doing this as a video rather than doing it in class. There were 4 problems. Let's down to problem number 1. We get used to this scrolling. It says use Newton's method to find the smallest positive value of x that satisfies the equation sine of x equals x squared. And so and we're going to use a starting guess of x equal 0.6, and I asked you to perform 3 iterations of the method. It took a fairly large starting value of 0.6 to stay away from the trivial answer, which is x equals 0. So I worked that out in advance. Now, of course, to turn this into the form of a root finding problem, we need some function of x equal to 0. And so we'll transform this equation, sine of x equals x squared, into the function sine of x minus x squared. So our function of x is sine of x minus x squared. Of course, I could change the entire sign of this thing if I wanted to. And to do Newton's method, I need the derivative of the sine of x minus x squared. The derivative of the sine is the cosine. Derivative of minus x squared is minus 2x. And so my working formula for the Newton's method is the new value of x is equal to the old value of x minus the function evaluated at x old, but divided by the derivative evaluated at x old. So given x is equal to 0.6, plugging that in here, and evaluating the sine of 0.6 minus 0.6 squared here, and evaluating the cosine of 0.6 minus 2 times 0.6, that was the derivative function. Evaluating that, plugging in the numbers, getting a first iteration value of 1.146. So we went from a 0.6, we jumped over the answer, because the answer happens to be very, very close to 0.88. Then taking the 1.146, we plug that in here, here, and here, into the function, into the derivative, and we get a 0.9321. And taking the point, that's our second iteration. And finally, our third iteration comes when we plug the 0.9321 here, and here, and here, getting a value of 0.8801 to approximately 4 decimal places. Probably the 0 is good and the 1 is not. Would be the third iteration. We could continue on a few more iterations and probably stabilize out to a neighborhood of a 0.87 something. But I didn't ask you to find the answer. I asked you to approximate it with 3 steps of Newton's method. Our next equation is we have 5 xy data pairs. Okay, and we're going to do some but not all of the work necessary to fit a cubic spline to that data. Okay, notice we have 0.0, 0.1, 0.2, 0.3, and 0.4 with things counting from 0, and that gives us our 5 data points. The x value is a 2, the x value is a 3.5, a 5, a 6.5, and an 8. And you can see from that, that's going to give us a step size h of 1.5. That's our delta x values. And then we have our y values. And for this cubic spline problem, we know the slope at the beginning and the end in this formulation. So at x is equal to 0, our slope is 0. And at x is equal to 8, our slope is minus 3. And so we know our slope at the beginning, and we know our slope at the end. And so the first thing was to write the equations needed to solve for only 3 unknown slopes, because we know the slope at the beginning point and we know the slope at the end point. And so we can set this up as 3 equations, 3 unknowns, or we can set this up as 5 equations, 5 unknowns. I've shown you both methods. Either way, here's our pattern equation, and this will be solved at j equal 1, 2, and 3, 1, 2, and 3, because it cannot be written for j equals 0, because it would refer to a j minus 1 term. Okay, and it can also be solved at j equal 3, because there's a j plus 1 term, 4, but it cannot be solved at j equal 4. So here are our 3 equations, making note that k0 was given as 0 and k4 was given as minus 3, taking each of these 3 equations, crunching the right-hand side numbers, and looking specifically at j equal 1, centering it on this point, We need function value to the left and right subtracted from each other, but they're both 4. That gives us a 0 out of this term. When I'm writing the equation at j equal 2, it's going to be a 30 minus the 0. Writing it at j equal 3, it's going to be a 0 minus 4. Will help flesh out these terms. Combining this constant that is known with the constant over here gives the equations packaged in this form. You can see the 1, 4, 1 pattern in the middle equation, but the pattern is always interrupted at the first equation and the last equation because we know some of the constants. So here's the equations in that pattern. Now I have claimed that the K1, 2, 3 answers are given by these numbers. How can we show that it's true? Well, this equation says matrix times my unknown k's must equal the right-hand side. If I now plug in my known k's right here and do the multiplication, I should get that right-hand side. So I take my matrix, I plug in the 3 given k's, I do this matrix multiplication, and I get a 0 and a 60 and a minus 5, which matches the right-hand side. So it does appear that these are in fact solutions to the set of equations. Now I asked you to compute the value of the cubic spline at x equals 4. Now there's a whole lot of work required to draw the cubic spline. I did not ask you to do that. I'm asking you to calculate one value of one spline at one point. And we do have multiple spline equations. We in fact have 1, 2, 3, 4 total spline equations, because we have 4 intervals between the data points. And now the particular spline equation we're interested in is at x equals 4. Well, this spline, the first spline, is between x equal 2 and x equal 3.5. The next spline is between 3.5 and 5, and that's where the 4 value would lie, between 3.5 and 5. The next one would be between 5 and 6.5, and between 6.5 and 8. So we want our spline equation that starts at the point number 1 and transitions to point labeled number 2. And that's going to be the j equal 1 spline from our generic equations for the coefficients and our generic spline equations, j equal 1. So I want to find all of the row 1 a values. A11, A10, 11, 12, and 13. Knowing that j is equal to 1 lets me pick out the right things. So A10 is f sub j, which is f sub 1, which is the second f, which is 0. And A11 is k sub 1. Now K0 was 0. K1 is minus 4.375. Write it down. Those are the easy ones. The next two have a little more work involved. I've got to crunch some numbers. A12 is 3 over h squared, 4 minus 0, and then minus 1 over h times this blending of the points. And here's the A13 equation. Go look it up. I now have my 4 coefficients, A10, 11, 12, and 13, having values 0, minus 4.375, minus 0.5, and positive 3.46. I take those coefficients and I put them here, 0, minus 4.375, minus 0.5, positive 3.46, times a linear term, a constant term, a linear term, a quadratic term, and a cubic term. All of these would be 4 minus the left value of the function, the left value of x, 3.5, to the first, second, third power, gives a value of minus 1.88. Okay, so we have evaluated the spline at only one number, which does not let us even come close to plotting it. That would be a lot more work. Problem number 3, we have a differential equation that says y prime is x times the cosine of y, with an initial condition that says at x equal 1, y is equal to 0, or y of x equal 1 equals 0. So we want to estimate the value of y, which solves the differential equation, using a single step of the RK4 Runge-Kutta fourth order method. And so since we're going from x equal 1 to x equal 1.5, we'll have a step size of 0.5. We were told that at x equal 1, y equals 0. And now we will proceed through and solve for, using the run to cutter fourth order method, solve for the k's and solve for the y's. So k1 is h times our function x cosine of y. X is 1, y is 0, and we get a 0.5. Now we're going to take k2 is 1/2 of our slope function evaluated x plus h over 2. X is 1 plus h over 2, which is 0.25, times the cosine of our y plus k1 over 2. That's a 0, that's not a theta, that's a 0, plus 0.5 over 2. The 0.5 just dropped on down and got a 0.6055. The k3 equation is the same as the k2 equation, except it uses k2. So 0.5, the 1.25 is here. The cosine of 0.6055 divided by 2 gives us 0.5965. Now finally for the k4, it's different because we're going to use x plus all of h. 1 plus all of 0.5 gives us 1.5. We're going to use all of k3 rather than dividing k3 by 2. 0.5965 is inside the cosine, giving a 0.6204. We have our 4 k values, blend them together with a 1, 2, 2, 1 pattern, dividing by 6, and we get a value for y at x equal 1.5 of approximately 0.5874. And then just to make sure you knew what to do next, I wanted you to calculate a couple of k values for me. So in the next step, x becomes 1.5 and y becomes 0.5874. H still has a value of 0.5, so the next step we'll be heading toward the x equal 2. So k1 is 0.5 times the current x times the cosine of the current y plus nothing gives a 0.6242. Here's the next important step. K2 is equal to the step size times the current x plus half the step size. Okay, operating the cosine of the current y plus half of the previous k1. That's sort of the big final step, getting a k2 of 0.5442. That's as far as I asked you to go, and so we end that problem right there. To get all the way to getting a value at x equal 2, we got 2 more k's to calculate, and we'd have a blending to calculate. Okay, problem number 4, a finite difference, steady state, so time is not involved. Steady state heat conduction problem. Okay, delta x, delta y are both 0.15. I've shown the unknown temperatures, T1, T2, T3, and T4 is my naming convention, and the boundary temperatures are given. So we've got 4 unknown temperatures and all the boundary conditions necessary to estimate the steady state value of these. The equation that we can write is that this temperature plus times minus 4 plus the sum of all the temperatures around it must equal 0. And that's true for T1, T2, T3, and T4. So the equations we write, so for the T2 value, it'd be minus 4 times T2, and then its neighbors would be a 50 and a T4 above and below, and a T1 and an 80 left and right, letting us write that equation. We write each of those equations. Then I said, solve those equations for the 4 unknown temperatures. You can solve them any way you want, including using a Gauss elimination, and many of you did, and that takes you to the actual solution, not an approximation of the solution, if you do everything right. But I thought this was probably faster to just set these up in a Gauss-Seidel form and do 2 iterations forward using a starting guess of 30 for all the temperatures. And I did the Gauss-Seidel without rewriting the equations by placing 30s written in small numbers in each of these boxes first. They had nothing but 30s in them. And then I now know that this equation says put a new number in this box by averaging the 4 numbers north, south, east, and west. So I want to average 50, 10, the 30 that was there, and the 30 that was there, and I'm going to get a, so add the 4 numbers together, divide by 4, and I got a 30. It didn't change this number. Move over here, and I'm going to take the 50, the 30 that used to be there, and the 80, divide by 4, and get a 47.5. go to this box, take the 30 that is sitting there, the 10, and the 30 that was sitting there, because this one was semi-empty at the time. Average them together, get that 20, average these neighbors, which would be averaging the 47.5, the 20, the 10, and the 80. Average those together by add and divide by 4, and come up with the 39.37. I took these four numbers and I wrote them very small in the lower right hand corner of these boxes, and then I did the average of the neighbors of this one using the values that drop down here. Then I moved over to the next one, but this new average included the 31.87. Moved over here, but this new average included the 31.87 as well. Moved over here, but this new average included the 47.5 and the 22.81, etc. And then with the numbers I got here, I just copied them down here and said that's my answer. This is a fair approximation of the answer after 2 steps of Gauss-Seidel. I didn't write down the answer if you actually used Gauss elimination and solved them precisely. It wasn't terribly far from these answers. Okay, so that is the solution of the exam. Now, of course, in a Gauss-Seidel way, we could have solved each one of these equations for the term that had the 4 and done a more formal Gauss-Seidel. That's a perfectly fine way to do it. This pattern might help you, might simplify it a little bit just by looking at the pattern rather than looking at the equations, but whatever works for you is fine. So that's the solution to the exam. I would like to be sure that you come talk to me, contact me about any questions about the grading of your exam, and let's try to get that resolved within the next calendar week. Okay, that'd be the end of this video.